Okay, so I'm going to share my screen now, and we'll talk about hypothesis testing, which will basically take us through this week. And next week, we'll actually talk about linear regression. The idea is going to be focusing on linear regression, and most of the project will be focused around linear regression, but it does help to talk about hypothesis testing. So these notebooks, right, are all on the repo. I don't have to show you guys where to find it, but probably stats and experimental design. So it kind of talks about first, like when we're doing hypothesis testing, the first thing is to talk about like you can't make a good hypothesis. You can't do a proper what we call A/B test and stuff like that without having good data. And the only way to get good data is to make sure the experiment is actually well designed first. If your experiment in collecting data is biased in the way that like it prefers a certain segment of the population just by how it samples, you're not going to get good results from your experiment. So I just wanted to quickly review that good experimental design using a scientific method, making good experiments, control groups, random trials, sample size, reproducible. So the idea here is I'm not going to go through all the details. There's some details in the curriculum, but the main thing is to basically like if you know your data is coming from the scientific method, you actually are designing a good experiment that actually tests what you care about. That's kind of a subtle point, but it's kind of important. These two parts are going to be your first like initial like, hey, if you don't have this set, like you're not going to have good results, or it's unlikely for you to have good results. I used to be a science lab teacher for middle schoolers. And this was like something I had to like drill in everyone's head. And I'm sure you've seen this before, but like it's helpful to kind of think about like, having the scientific method put in your actual process. And even if it's sort of something very simple that doesn't seem like science and stuff like that. Control groups, you always need a control group. You always need something to compare it against. If you don't have something that hasn't changed and you just change it all, you don't know if the results you get are because of the change you've made or it's just something that was already part of the group. So you always need to have that control group. We'll talk about A/B testing, but one class of A/B testing is like, how many people will click on my site or click on this web page, or like let's say YouTube. YouTube's an easy one because this happens all the time. YouTube has a little thumbnail of the video, right? And all the person sees the thumbnail and the title. And so you want to do A/B tests to say, hey, if I change the image from this image to this image, will someone click on this? Will someone click on this video more? If you change the image and you see more clicks on it, you might assume like, oh, well, I changed it, therefore there's a bunch of clicks on it, so therefore the change was a good thing. But maybe, for example, you got more clicks just because of the nature of, people saw your video more and whatever, and we're going to click it regardless of if you change the thumbnail or not. So that's why it's important to have that control. Say, don't change anything, and then have a change, and then see if the difference between those two. Random trials. So again, the idea here is that you hopefully will get a random sample of the population that you are targeting, right? So you want to make sure you don't get basically a bunch of new users versus a bunch of old users. This is also kind of built into a little bit of control groups, is that if you test like before and after, you are getting a new segment of that population. You're getting the before segment and the after segment. You want to make sure that's distributed equally. So what classic you do is if you have the control group in the experiment group or experiment groups and have those available for each at the same time. So you hopefully get the same random sample. Sample size, obviously, if you only ask 5 people if they clicked on this video because of the image, or like they see, 5 people is not going to be enough to really get an idea of what's happening. So you have to make sure you have a decent sample size, which we'll talk about with statistical power in designing an experiment and actually saying, all right, if we have statistical power in this effect, how many people would we expect we need to test? And it turns out this number can be actually pretty decently low, which is kind of nice. Reproducible, basically you got to make sure you have your experiment so you can reproduce it and change it and like actually scrutinize it. If it's not reproducible, it's going to be hard to actually like do a good experiment and all that good stuff. Okay. This has nothing to do with data science by itself, but I think it's helpful to look at like classic experiments. Healthcare triage in particular, it's this YouTube channel. It's actually a very small like YouTube channel. I don't think too many people actually watch it, but the host does a really good job talking about different experiment designs. In this case, centered around health and like health analysis, and they talk about analyses. I think it's a really great channel if you're kind of curious a little bit of seeing some like what those experiments look like and like when we talk about experiment design, like, because a lot of times in data science, we don't have control over what sometimes you do, but we might have control over like, can I make these adjustments? It's kind of like already set in stone, like the data are the data are. There's a really great job of taking data that's already been put together. And the thing that's like hardest for, especially for health studies, is random trials. Like random trials are really, really hard to come by. And so you can actually you can still do quite a lot, but just keeping in mind that's not random. And I think this host in particular does a really good job of explaining that, like situations for meta-analyses. So if you're curious, check out this YouTube channel. I would search for meta-analyses, like his videos. They're usually less than like 10 minutes. And I think it's a pretty good idea of how this can actually be useful. Okay. Cool. All right. Won't take any more time on that for experimental design. Hopefully that all makes sense. I think all this seems pretty intuitive, or at least yeah, nothing sounds bad about this. Okay. So moving right along, statistical tests. So once we actually design an experiment and we want to see we have a control group versus a experiment group, we actually want to see a little bit well, how do we know that they're actually significantly different? This is where hypothesis tests, statistical tests come in. So the first thing we do is kind of this defining is that we have a hypothesis. I don't know if you all it's been a while since you've taken a science class or whatnot, but if you hear hypothesis, right, this kind of the one that pops in my head is I remember hearing my teacher going, an if-then statement, right? If this happens, then this happens. That's kind of the idea of a hypothesis. The null hypothesis is really saying there isn't any difference between the experiment group and the control group. Note that we can also have multiple experiment groups, but the idea is we have an experiment group, we have a control group, and that there's no difference when we have the treatment. The treatment is the change, the difference between the control and the experiment group. And so the idea there is that the null hypothesis is nothing happens. We assume the null hypothesis is true. We say, if we make this change, if I switch the thumbnails on the video, nothing changes. Or at least there won't be an effect that's measurable. That's what the null hypothesis assumes. Okay. Make sense? Cool. So note that we usually denote the null hypothesis as H sub 0. So that's kind of saying oh, the null hypothesis. And this is actually important, as that I would say, write out, even as a data scientist, write out the null hypothesis, make sure it's clear what the hypothesis is. The alternative hypothesis, so this is basically with the experimental group, is saying the opposite of this, is that basically saying that the experimental group is different since the treatment has an actual effect. Basically, you're saying, hey, there was an effect when we made this change, the treatment. Okay, we made this change, so they are different from each other. Note that this notation usually is H sub A. Usually I see H sub 1, depending, depending on the industry, where their academics come from, they might do either one of these notations. But the idea there is the alternative hypothesis is kind of the opposite of the null hypothesis. Now I put a little warning here because these hypotheses only care if the effect is significant, not how strong the effect is. So that's kind of a subtle point, is that just because you disprove the null hypothesis, which means the alternative hypothesis is the likely answer, does not mean that it is a stronger effect. There might be a requirement by how many people you sample across, but the hypotheses themselves do not signal on how strong the effect is, just saying that there is a statistically significant effect. And statistically significant basically says it passed the test. But it's entirely possible that you just randomly came across certain individuals, the people that you tested, and they all just happened to do a certain thing that was not true in the total population. So you always have to be careful about saying what was there an effect there or not. It's well, we know there was an effect, we don't know how strong that was. When we formalize this, we'll actually look at alpha confidence, or basically our not confidence, our significance level. And our significance level will basically say, well, how big of an effect do we have to see for us to say it's statistically significant? It doesn't mean that effect is as strong as we say it is. It just says that there was a significant effect where we can say this is likely, there likely was an effect from the treatment. Okay. Now you'll hear me talk very specific in words and stuff like that. And that's because I want to make sure I don't say the wrong thing and, have you poison your mind with the wrong terms and stuff like this. So this is kind of where it's coming from. But yeah, does this all make sense? Null hypothesis, alternative hypothesis. Thumbs up if that makes sense. Cool. Chuck, you had a question.
Yeah, a question. So I've come into this scenario before. I was wondering how you may set this up, but let's say when you're doing the test, like the business has said that they are, based on like a financial model or something, that they have to see an increase of X. Maybe it's 25% more people visiting the web page or clicking on that icon or something. Would you put that 25% goal or lift goal in the alternative hypothesis, or would you measure that a different way?
Yeah, that's actually a good point. And that's actually going to tie really well into what we call statistical power. Statistical power will actually tie in the sense of like, what is the effect that we would need to say it's significant enough for, like, I should say it's valuable enough for us to make this change. Because there, for example, if I lower that, that effect size to a very, very small effect, I can say it's statistically significant. There is a significant difference between these two groups, but it doesn't tell me that it's worth it. So it will actually not tie into the hypothesis. It'll actually tie into our confidence interval, and for A/B testing, it'll actually tie into saying, okay, if we want this effect and we want this confidence in it, our significance, like, how significant it has to be for us to be worth it, how many people we have to sample across. And so it turns out the number of people we sample, how big the effect that we hope to see, which is tied to statistical power, and how confident we want to be with our results, those three together will tie together. And it turns out they're mathematically related to each other. If you adjust one, if you want a bigger effect and you still want a 95% confidence, well, guess what you have to do? You got to increase the number of people, because you have to make sure that you have enough people to make that claim. If you only have availability to test 1,000 people, and you want this confidence, it means that you have to settle for the fact that you might catch only this effect size, and then that'll be significant. Like that'll be the only significance you have. So each of these are kind of like three dials that you can kind of turn a little bit. And usually what it is exactly what you said, Chuck. It's like you're looking for a certain effect because you're like, hey, it's only worth it if we see this difference. And if we see this significant difference, that's what we really care about. In that case, you're probably going to have to sample more people. Cool. All right. Good question, by the way, because that'll lead directly into what we care about. Okay. So going a little bit, again, like, when can we say there was an effect, right? Remember, we're just making this hypothesis, for now, I'm kind of skipping over the idea of like, how do we define this effect, but saying, okay, there was an effect. And then we conduct the experiment. We need to figure out, if there actually was a difference, right? If there is significant, we call it statistically significant difference. So this is where p-values come in. So who's heard of p-values before? Just give me a thumbs up. Yeah, this is a very common statistics thing. P-values can be very confusing. There's also a lot of things that can be misinterpreted from p-values. There's actually this great article from Hacker Noon. The author, I can't remember the author's name, but they actually, I believe they still work. I think they still work with Google right now. But they talk about this idea of p-values and interpreting, like, what does it mean by p-values? So I'm going to send this in the Zoom chat just to have you guys be able to look at this later. Definitely look at that after our study group. But I kind of like, they talk about puppies and p-values, which I kind of like. And basically the way that's phrased, and I think it's a really great explanation, is that basically what a p-value tells you is how strange do things have to be if the null hypothesis is true. That's what a p-value is really saying. It's like, how strange would this situation be if the null hypothesis is true? And they talk about, like, I don't know in the details, but basically the idea is like, you come into your home and you see your house is trashed, and you see, like the little trash can over the dog's head. And you're like, well, the null hypothesis is that the dog didn't do it, well, how strange would things have to be for the dog to actually not do it? And you can think of a whole bunch of contrived, scenarios that could have happened. And that p-value, though, is very, very small because it's very unlikely that the dog didn't do it. It's more likely based on the evidence that you have. This is basically your test, the data you have. It's very unlikely that the dog didn't, or very unlikely the dog didn't do it. So that's the idea of p-value. Okay. Critical values. So this is kind of like related to p-values, but it's usually we start off with critical values when we actually create these things and we get p-values out of our test results. So critical values are how weird things can get before we reject the null hypothesis. So what I mean by that is that we'll set a critical value that says, all right, the critical value has to be at this level. And that's actually directly tied to the confidence interval. We say, okay, we call it alpha. Sorry, this notation's kind of getting funky. There it goes, alpha. Okay, it looks like a little a. Basically, we set alpha and say, okay, things have to be this weird before we can say we can reject the null hypothesis. If you guys remember back to Wednesday when I talked about standard deviations and stuff like this, and I talked about medical tests and how many standard deviations they need versus like, particle physics. I said like you need 7 standard deviations in particle physics for them to declare a result happens. Basically, the reason why it's standard deviations is basically their alpha is very, very, very small. Like they need a very, very weird thing to happen before they can claim to discover. And that's partly because of the nature of how particle physics works. Is there's a lot of weird things can happen because you try so many different things over and over again. So that's the idea of this alpha. Now, usually what we do, we'll take our alpha, we set that ahead of time and say, all right, we need this alpha to be this value. And that's determined by how many people you want, what the effect size you need, and all that good stuff in the confidence interval. So you have this alpha, and then you say from alpha, you say, okay, I need it to be, we'll say like the classic is like 0.05. That's my alpha. If my p-value is less than alpha, then that means things were really weird from my data that I've already said, hey, if things are less than 0.05 for my alpha, then I can reject the null hypothesis and say the alternative hypothesis is likely true. So basically that's kind of telling you, saying how weird can things really get before we say null hypothesis is probably not true. The dog probably did, ruin the whole place or whatever it is. Okay, or, oh, people clicking on the video actually was because of the thumbnail change. Okay, does that make sense to people? Yeah, thumbs up if that made sense. I was like, oh. Okay, so the main thing from like alpha, I just want to reiterate, is alpha is something you set ahead of time based on your needs for the experiment. The p-value comes out from the actual hypothesis test, and then you compare those two. Okay, and that alpha is signaling how weird do things have to be before we say it's not the null hypothesis. There is an actual effect. Versus the p-value is the thing like how weird were things actually. Okay, so that's a little subtle difference, but it's important. So classically, this is from XKCD. I don't know if you guys kind of look at this little comic. The p-value versus interpretation of the p-value is usually people say, oh, we get a very, very small p-value, less than 0.5. It's like, oh, highly significant. You can see here 0.5 is usually, 0.05 is usually what we're looking for. So significant. And then usually it's like, oh, as we get higher and higher, people kind of like change things up and how they interpret it and stuff. Classically, if you get p-values in these high parts, you really can't say anything about the alternative hypothesis, or really the null hypothesis. But that's when people kind of like try to change things up. So just thought it was a kind of funny thing as you guys try this out. This is where I will say is like, just because you get a weird value does not mean it is significant, or at least significant to what you care about. There's this famous cautionary study of weight loss with chocolate. Has anyone heard this before? It's something like chocolate or dark chocolate, eating that can help you like lose weight, like more than like, chocolate. Yeah, see, Bulla, okay, he gave a thumbs up. It's usually someone who's kind of heard something like that. It actually stems directly from this study, which again, I'll have the link here for the actual paper. Like it's an actual paper that was published on the journal. And there's actually a really great interview or article, I think it's a partial interview, an article about this on on this exact like situation. But I'll just very briefly say what happened is that the statistician, or I actually don't know if he's a statistician, but this person said, I'm going to do this study, and basically openly said, I'm going to do a study that this will make headlines, this will be published by a journal, but it will not be factual, in the sense that like it will be statistically significant, but will not really be truthful to how the real world works. And what basically did, they conducted a study where they took a small number of participants, I think there was like 7 people in total, and they tested them on many, many different like attributes of, like things that they can do, as well as different things that they can measure, like their heart rate, their how much they weigh, like all these different attributes they could say. And basically they knew that with all these attributes and all the different things that they're going to measure, like things you can do, like treatment trials, eventually something will come up. Because remember, you're just basically playing the odds. Is that eventually, if you are, or if you're lucky enough or unlucky enough, you'll find a random sample that basically is significant, even though it really isn't. or I should say, it's a really extreme value when really you would expect more of an average value. So that's what happened here. And so this is actually what we call p-hacking, or at least one version of p-hacking. There's a few ways we can like hack a p. So the p-value was actually significant, but it turns out it was not actually truthful. So in this case, I love this little comic because this is really perfect. The idea here is that jelly beans cause acne is the claim. And so they hire scientists to actually check this out. And so basically what they do is they first say, oh, we found that jelly beans in acne, it's not significant enough. A p-value greater than 0.05. So their significance value is 0.05. And it's like, he's like, oh, okay, like that means jelly beans don't cause acne. And then someone says, wait, I think it's a certain color. So what's happening here, like, as you might guess, jelly beans probably don't cause acne, right? It's probably not significant or probably a direct causation. However, if you redid this experiment many, many times, right, and it is insignificant, every once in a while, you might actually get a p-value that is significant because there's a random chance of how, like how you measured things. And so that's actually what happens here, is that basically each color is not significant. There's no real difference between a purple jelly bean and a brown jelly bean and whatnot, right? So they end up performing this experiment over and over and over again. And then this little panel right here, if you look at it, it's actually one of them, like the green jelly bean has a less than 0.05%, so basically it's statistically significant, but everything else has no significance. And what's really cool, this person's super smart, the person is XKCD. If you look at the numbers right here, if you see how many panels are, there's actually 20 panels on here. An alpha level of 0.05 says that if you do this experiment about 20 times, 1 out of 20 times, 5% of the time, you'd expect a significant result, even though it's not really going to be significant. So it's actually really truthful. It's like, oh, you would kind of expect about 1 out of 20 times that you'd actually see a real result. And of course, then the punchline is that this becomes news. And so this is my thing, is like, you can do this. Like, this is where p-hacking people purposely do this sometimes. Some people don't realize they're doing this. But my goal for you all is, when you're doing hypothesis tests and A/B testing, when you tell someone, hey, this is significant, if like you're starting to do things that might not be, that might show one result that really doesn't actually exist. So that's kind of like my goal for you all. But this is kind of the cautionary tale of like what you should be careful of. Okay, but summed up in a nice little comic. Okay, cool. All right, I know I'm going pretty quickly, but how are you feeling? Pretty good? Okay, I talked about everything very abstractly. Now we're actually going to start diving into a little bit of code and actually doing some stuff, right? So yay, code. I actually don't know if I go into straight at code, but I'll kind of show you a little bit what we're going to talk about. So I talked about the significance level, hypothesis testing. The first thing that we're going to do is, I mentioned way before, like z-test, c-statistic. I didn't go into details, but I kind of mentioned it. That's the first way. We are not, I'm going to tell you right now, I'm not going to focus on z-test, because a z-test is relying on a normal curve, and it turns out we can actually do better than a z-test. We actually will look at t-test and Welch's t-test eventually. And I will tell you is that, I'll just tell you up front right now, do a Welch's t-test. Like, it's a little more conservative in the sense that like you might get some more false negatives, which means it's like, oh, there was a significant effect, but we didn't quite measure it. But that's okay. I would say that the Welch's t-test in particular is pretty good at actually performing this. Like, normally that's what we would do. So anyway, the main thing is that you can kind of think of this z value, which will kind of translate to t value later on, is basically how far away x minus mu divided by sigma divided by the square root of n. You're like, whoa, this math, right? Like, what's going on? Basically, it's saying if you take x bar, which is your sample mean, how far away is your sample mean from the population mean, divided by standard deviation. And basically, this is saying how many standard deviations is your sample mean from the true population, is kind of what this is. And the thing about the square root of n here, it's like, well, what's that square root of n? Is that if you have a larger sample size, that the chance of you getting on those very extreme values gets smaller. So the larger your sample size, basically the smaller this overall value is, which makes your z value significantly larger. So basically the idea there is saying that, oh, if we have many people in our sample, it's more likely that we'll get a value that's very, very close to the true population mean. Okay, and that's really all it is to it. It's basically you calculate this from your you can calculate the sample mean, you can have the standard deviation, You can have the population mean, which I'll talk about like where you get this population mean. But if you have all these parts and you basically get a z-test or a z-score, and that z-score then translates over into a normal distribution, which says, all right, what is the p-value for this z-score? And then that you basically from there say, oh, is it less than alpha? So it's actually not a very difficult thing. It feels like a lot of different steps, but it's actually like a very straightforward test. At least I find it pretty straightforward once you get the hang of it. So our goal basically will be measuring this, what we call a statistic. In this case, it's our z-statistic, our z-score, okay? And that will basically translate into a p-value. And with that p-value, we could say, okay, is this weird enough for us to reject the null hypothesis? All right, so what this looks like is we have a null hypothesis. We say assume nothing, like assume nothing new, no effect. Then we have an alternative hypothesis, has an effect. And then what we do is we attempt to reject the null hypothesis. This is where I like to say, some people will say, and you'll hear people say it, plenty of times say, accept the alternative hypothesis, or accept the alternative hypothesis, or reject the alternative hypothesis. That's not what you do. You always are trying to reject the null hypothesis, and what you'll have two outcomes. You'll either reject the null hypothesis is likely not true, or you say, I failed to reject the null hypothesis, which basically is saying like you couldn't disprove the null. Okay, it doesn't mean it isn't like the effect isn't there. It's just we just failed to reject it for this instance. And those are kind of like two outcomes in there. And essentially what you want to do is you want to, like, your goal is hopefully to actually be able to reject the null hypothesis and say, oh yes, the alternative is likely true. So it's a little subtle, but it's something I thought I'd throw in there. All right, so this is essentially what you're doing. Is you have a distribution. In this case, we're looking at a normal distribution. Later on, there'll be something called a t-distribution, which is basically a normal distribution with a slightly modified shape. It's very similar to the normal distribution. And basically you say, hey, like we want to see if our value falls into one of these tails. So usually we say, oh, for example, let's say it's the average age for, I'm trying to think of a good example. So we talked about the Titanic. We saw the Titanic distribution of age, and we pull out someone who is, I don't know, say first class on the Titanic. And we say, okay, we pull out the first class. Say, is that person we pull out from the first class, is that person's age significantly, are they significantly older than the average person on the Titanic? And that's essentially what we're doing. Say, hey, do they live in this area? In some cases, you might pull out someone's like, oh, really pull from first class. Is that person significantly younger than the average age of the Titanic? And that would be the situation here. So basically you're saying, oh, I don't really like mu here, but like, is our value, our sample mean significantly larger than what we expect if there was no effect? Okay. And then that's what we say one tail test, which is basically one of these situations. A two tail test basically says, is there a difference? Is it just different? So you can say, if I take a first class person, first class passenger, is their age statistically significantly different from the average age, which means they might be older or they might be significantly younger. So we exist in two tails here. And so in this case, basically, you're going to be looking at saying, is it in both of those parts? And usually denote this with like does not equal to. Okay. And that's the only three situations that you have in all hypothesis testing. Is basically, is it greater than the average? Is it less than the average? Or is it not equal to the average? Okay. And those are really the three situations. Okay. So hopefully this is all making sense. I talked about the p-values for puppies. This right here is kind of, I think, a more kind of like this is close to like what we'll actually do. And it's kind of like, we'll do this on math. We'll never really plot this out, but it helps to kind of understand what's going on. This right here represents like the actual like the sample means. So remember when we did the CLT, central limit theorem, we did a bunch of samples. You can imagine that this is the distribution of all the possible samples we'll get. Most likely, if the null hypothesis is true, meaning that there's no real effect, we likely would fall within what we call like mu, our population mean, okay? But let's say we're talking about very extreme values. These are very, very unlikely if the null hypothesis is true. And this value right here, you can see it says 95% in this like dashed area. This right here basically says, at this point, if we get values over to the right of this, we say that's a really weird result if the null hypothesis is true. Therefore, if we get values that are in this, like, off to the right here, these are so unlikely that the null hypothesis probably isn't true. It's probably something else. And that's kind of the idea here. And this green spot is our sample mean, or, in this case, our sample mean. This is our sample that we actually care about. It's like, hey, like we look at this spot and you say, hey, this is a really unlikely result. So that's kind of where we have our value here. And the way we calculate this, like, well, how do we say, like, in this value, we use p-values to basically express this. And that p-value, all it is basically saying, hey, from this point here in weirder, that area underneath the curve, that is the p-value. In this case, might be like, 0.04% of the total area underneath this whole curve. That's what a p-value really is. It's just this area. But that's how we express it. It's like, okay, we have this point here. What would be the area underneath the curve for under this under the null hypothesis distribution, essentially? What is that area? And say, okay, compare it to this guy right here, which will represent, in this case, let's say 95% statistical significance level. That will be 5% of the population would be found in this weirder area. If this area is smaller than this area, then we say, oh, that is statistically significant. And we say the null hypothesis is likely untrue. We reject the null hypothesis. Okay. Does that make sense to people? Okay, I'm kind of breaking down a whole bunch of things. Chuck, go ahead, get a question.
Yeah, just to confirm, so this graph would be the sample, the mean of the sample mean?
Yeah, it'd be like all possible means for every sample. If we had, like, let's say a sample of 100 people, like if we took a sample of 100 people, what would that distribution look like if we took 100, like, you took 100 people, I took 100 people, and we compared our samples, our means of that sample, we'd fall somewhere in this distribution. Does that make sense?
I guess and I was trying to get to is, does that, for it to get into that, 5% tail, the significance shaded area, does that mean that the mean of the sample was 2 standard deviations greater than the population? Or
yeah, yeah, and you can think of the population mean as being like, what would the mean be if there was no effect, if the null hypothesis was true?
Right. Okay.
Yeah. So there's a few ways to get, like, in reality, it's hard to get the true population mean. Like, how do you measure that, especially if you're trying to do a random sample? Usually, for there's ways to get the idea of that sample, that population mean, and usually we estimate that from other information. So that's the kind of idea there. Yeah, cool. That made sense. All right, cool. Yeah, there's a lot of different parts in this, but I think once you start breaking it down, like, honestly, like, the math is really simple to do. Like, it's going to be like a few lines of code to actually, like, perform a hypothesis test. But the money isn't about performing the hypothesis. It's usually the interpretation of the hypothesis test, which is kind of why I'm being so pedantic in a lot of ways of really showing you all these different parts and, like, kind of breaking it down, because that's really where understanding what the results are going to be the significant part. Okay, cool. All right, cool. I'll kind of move on. You've seen these two graphs, or these two different comments before. I'm going to show you a little bit of, like, how we would do the hypothesis, like actual hypothesis tests, and, like, one sample z-tests. I don't want you to focus so much on the z-test itself. Just think of, like, once we have a statistic, in this case, it's going to be the z, like a t-test or Welch's t-test. But the process is basically the same exact thing. Okay, so what this does is, like, we have steps in doing this z-test. Step number 1, state the alternative hypothesis in the null hypothesis. So in this case, the sample mean is greater than the population mean mu. Okay, that's what you do. Step 1, state your hypotheses. Step 2, specify the significance level, alpha. So alpha is the probability of rejecting the null hypothesis even though it's true. So basically the idea here is that we're defining how weird do things have to be for us to reject the null hypothesis. And usually the classic is about 0.05, but it could be smaller, it could be even higher, just depending on, like, what situation you care about. Okay, so you basically determine your alpha and you have your hypothesis. So this is basically before you even touch the data. You don't do anything about the data yet, and all you've done is basically state what the hypotheses are, what's going to happen if you reject the null hypothesis, what does that mean for you, And then the alpha level, which we'll talk about statistical power, you determine this alpha level and say, okay, this is the alpha that we're looking for. Okay. Then we actually do the real work. Okay. So we calculate the test statistic. In this case, I showed the Z statistic, but note that we'll later to actually do the t-statistic, and I'll show you all how to like actually calculate that. It's actually pretty simple. And that basically we take this data, this statistic, and we say, okay, we calculate that t-statistic from the data, the sample data that we collected. Then from that t-statistic, we calculate our p-value. In this case, I'm showing you from a z table, but in reality, like we have computers. Like you basically give the t-statistic to the computer and say, this is the distribution that I expect it from. This is my statistic. Find the area underneath the curve using that statistic, and it gives you the value. Okay, and we'll show you how it's actually really easy. The simple, like one way you can do this is 1 minus the CDF of the normal distribution underneath given the z statistic. Replace normal distribution and z statistic with t distribution and t statistic, or whatever test you're doing. There's also like an f test. You can do the f statistic and the f distribution. You just replace those things and you basically find the area underneath that curve. Okay. Now, once we have that value, we have that p-value, and then we interpret that p-value basically saying, compare it with alpha. And basically you say, is p less than alpha? If it is, then you say, hey, it's significant to this confidence interval, or this confidence. So if we have like a 95, like if we have 0.05 for our alpha level, we would say there's a 95% confidence that we have a strange result because p was less than alpha. Okay, and that's it. So you can see like the real work really is, first of all, defining the parameters of the experiment. And then the real work is just really calculating this t-statistic from the data and then finding the p-value. But this is actually pretty automated. It's actually really easy to find. So I did have a little link to another instructor, Jeff, who does a walkthrough of the z-tests. But if you do the z-test, it's pretty much the same thing as the t-test. It's just a different distribution, a different statistic. Okay, so that's available here on this notebook. Okay, cool. For this kind of step-by-step, does this all make sense? Like kind of like those steps? Hopefully it doesn't look too scary now that you see like it's summarized in what, like I have 5 different steps. And that's really what it is. And some of these steps are actually much easier than what it looks like. So yeah, sound pretty good? Cool. All right. So I'm actually going to skip over effect size right now, and I'm going to go right into t-tests. Okay. Well, maybe if we have some time, we'll talk about effect size. So I'm going to show you a t-test now. So I kind of hinted already. I'm saying I'm not even going to talk about z-tests because why would you use a z-test when you have a t-test, basically? And the reason why is because it turns out t-test is basically a slight deviation from the typical, a t-distribution is a slight change from the normal curve. And so with that change, we actually can get better results. So we can actually use this t-statistic, which gives us a summary of the data. And then we can use a t-distribution to decide if we want to reject the null hypothesis. So let's see, we can use the t-test to compare sample means when we don't know the population standard deviation and large and greater than 30. So one other thing I wanted to show you is what the difference is between that t-test, t-distribution, and sorry, I'm kind of talking to myself and saying it out loud, t-distribution and the normal distribution. I'm just going to show you, I'm not going to go through this whole diagram. So this is actually a really great show right here, is that in blue, no, sorry, in blue is the actual normal distribution. And we have these things called degrees of freedom. So we'll talk a little bit like, depending how many people you sample, that's kind of like how many degrees of freedom you have. So what happens is that basically in the red here, and you can actually see it progressively changes, the green is like past degrees of freedom. This red one represents the t-distribution. So you can see here, it's got slightly fatter tails. And the reason why is because if you're only sampling a small number of people, you're more likely to get more extreme values because you only have to get one person. You know, if you're only sampling one person and you get that one weirdo in the group, right? They're more likely to be on this very extreme ends. So that's why it's more likely, we call these like have fatter tails. You can see it's more likely for us to get these more extreme values. As we increase the degrees of freedom, so you can see 1, 2, 3, 5, 10, 30. As you get close to 30, you can actually see in red, it's almost exactly the normal curve. And we say basically at 30 degrees of freedom and greater than 30, you have at least 30 people. We can say it basically is the normal distribution. So we don't have to like worry about it. And it turns out by realizing that, we can just say, oh, we have the normal distribution, close enough, like as long as we have a large set, which is basically more than 30 people. I'm going to show you really quickly like how to actually calculate this confidence interval. I'm using SciPy stats, and basically this stats.t.interval, you feed it in these 4 parts. So the first part is basically, what's the confidence interval I care about? 95%. What's the degrees of freedom? Note that's represented by df, not data frame. 99. So the confidence interval is basically 100, like the number of people minus 1. There's a little subtle difference, like reason why you do minus 1. Basically, like how many ways we can like change this degree of freedom. So in this case, it's 100 people. So 99 is the degrees of freedom. The sample mean, basically, what was the mean when we actually took the 100 people and sampled them? In this case, I'm like, oh, it's 65. You know, whatever you measured, right? And then the scale is the standard deviation estimate. And that standard deviation estimate is basically going to be represented by just how, like partially represented by how many people. If you have more people, your standard deviation will be actually smaller, your estimate. So the way we get standard deviation, this value here, is actually say, what's the standard deviation of our sample? How does our sample deviate? And then we divide it by how many people, excuse me, how many subjects or how many, you know, whatever we're measuring, how many subjects we have in that sample. So the idea is that if we have a sample standard deviation of like, let's say 10, right? But you have like 1,000 different, you know, members in that sample, then you know that it's relatively short versus if you had a standard deviation of 10, but you only had 10 people, you know that like you might actually have to make that a little bit wider. So once we have this guy, we plug these in, and that gives us basically right here our confidence interval. So our standard, remember our mean was 65. Basically, we have a 95% confidence interval from about 29 to 100. If you wanted that larger, you would basically, if you wanted more confidence or less confidence, for example, a 95% confidence, note that this is going to be a smaller area. But you can see, even from 95 to 99, it's barely bigger. You can see like these values got significantly bigger. Note if I put like, you know, 99, oh, sorry, I put the, sorry for the confidence interval. That's not bad. There you go. 99. You can see that this should expand outward. In fact, it gets pretty big. You can see 17 to 112. So that confidence is getting bigger and bigger because in order to have more confidence, you have to have more a wider range. Okay. So that's really how you can like calculate this this t interval, this confidence interval. But I'm going to show you a little bit like what the t-distribution looks like. So back to our hypothesis test with t-tests. We're going to go back and say, okay, we need at least n greater than 50, right? And we can see that's what we have this part right here. We'll have our different steps. First, get the hypotheses, our null hypothesis and alternative. You write them down, okay? Determine your significance level. Usually we say 0.05, but it can be different depending on your basis on effect size and statistical power. So just know that we first say, okay, this is our alpha value. You don't change the alpha value because if you change it, it means that you're basically accepting more or less weirdness to reject or fail to reject your null hypothesis. And if you do that based on what value you get in p-value, then basically you're looking at the results and then changing the result or changing your conclusion based on the results you had, if that makes sense. So you want to make sure you already have a good idea of where alpha should be. Get your t-statistic. So in this case, this is the actual equation for the t-statistic. Note that instead of standard deviation, it's a lowercase s. It's very small. But x bar, sample mean, minus mu, which is their population mean. And then you divide by this s, which is basically the standard deviation, a modified standard deviation, divided by the square root of n. Square root of n is basically the square root of the number of participants, right? The number of samples that are in, or number of subjects in your sample. Okay. And then once you have this t-value, you take that t-value and you basically are going to take these values. Like this is essentially what the computer is going to do. Is basically you take this t-value with degrees of freedom, because degrees of freedom kind of change how you calculate this because the shape changes. But let's say you have a t-value of like 100 is your degrees of freedom, and your t-value is like 0.85 or whatever. You can say, okay, I can reject up to a certain level. Now this is like the classic, like oh, there's a table. You look up the table, you look up the p-value, you see is it significant. You're not going to do this. But I wanted to show you a little bit. If you have done this in the past, that's what we're doing. And so basically what we're going to do is say, okay, we have our t-statistic. In this case, it's in red here. We have our critical value, or alpha, our significance level, right? is going to be in green here, and basically say, hey, is our t-statistic less than the t critical value? There's a couple ways to do this. So in this diagram, I kind of mixed up a couple things. I should really say your critical t value and your t-statistic. This is going to be different from your p-value and your alpha value, but really you should think of your t-statistic, you can convert it into a p-value, and then you can basically compare it with the alpha value. If instead you had your t-statistic, you can, and we wanted to keep your t-statistic for whatever reason, you can actually translate your alpha into a critical t value using the distribution, and then compare those two. But in the end, you're still comparing what you measured, which would be your t-statistic / p-value, with your critical significance level, which would be like alpha / your critical t values. Like, I guess it could be other, your critical value. It could be another, it doesn't have to be t value. But that's basically all you do. And then once you do that, good to go. So let's actually, the reason why I didn't show this part is because I actually just want to show you like Welch's t-test. So I'm not going to go to full details because we only have like 8 minutes, but just know that Welch's t-test basically is even better from the t-statistic. Basically, it assumes, like, the problem is what we call like the t-test, and we usually call this the student's t-test, which there's a whole thing of why it's called the student's t-test. It's actually really interesting, but we won't talk about that. Like, we'll go into that detail because we don't have time. But we have Welch's t-test because the student's t-test assumes the sample sizes and variations are the same for samples, which might not actually be true. As you get different samples, the sample sizes aren't necessarily the same. They might also have a different standard deviation from it. So we can actually just use Welch's t-test, and it corrects this little significance of like our different samples. And by different samples, I'm talking about like our control group versus our experiment group. The student's t-test assumes that your experiment group in your control group are actually equal to each other. Like the sizes and the variation, which might not actually be true. So you can actually just use Welch's t-test and it corrects for that. So you get this more complicated equation, but you just code this in essentially, x1 and x2. The x2 is replacing for your mu, your population mean. So in this case, your population mean is just your control group. So I kind of talked about like how it's very hard to actually find the population mean. You can usually either estimate it from like what you already know about the population, or you say, hey, let me just look at my no control group in my experiment group and use the control group to be my population mean, or in this case, like x2 bar. And so you basically get these values here where SI, so S1, S2 is the variance, or I should say, yeah, it's the variance. It's the variance of your sample 1 and then the variance of your sample 2, and divide it by the number of participants in each sample. So in this case, you can actually have a smaller experiment, a smaller control and a larger experiment, and still have adjusted for this nice t value. Okay, does that make sense to people? Like what's going on here, like why it's adjusted, or like how it's adjusted? Cool. Okay, I see mostly nods. All right. Now the biggest complex of this is actually like making sure you get the right degrees of freedom, which is represented by this lowercase v. This is approximately true. It looks really scary and stuff like this, but for the most part, you don't have to worry about it. I'm going to show you like what you actually do. So I'm going to show you how easy it is to actually perform a t-test with Welch's. And in fact, SciPy has it built in. And what's really amazing is that SciPy actually says, because the Welch's t-test is actually like so much like better, like it's actually really easy to like just set to a Welch's t-test. But if you wanted the student's t-test, I'll show you how to do that. So I actually wrote this whole function here, and this looks like, oh, I have to write this function. This is literally all you got to do. A and B. A is representing the sample that you actually collect. B is representing the other sample you already collect. So like imagine like your experiment group versus your control group. And what this basically says, stats.t-test ind. You give it its 2 populations, and this will tell you basically what those what's it called? It will actually tell you 2 attributes. It will tell you the, I'm trying to remember the order of this. Might be better, but it'll tell you the significance level and the p-value. So if I do this, I'm sorry, not your significance level, your statistic, your t-statistic, and the p-value for that t-statistic. So just to show you a little bit, I have these two different distributions. We can go over them a little bit more. But you can see here is that I have our t-statistic and our p-value. So our t-value, maybe it just helps a little bit if I just go like this so you guys can see. I know we're a little short on time. That's why I'm kind of hopping around a little bit. This is what you get. Your t-statistic is your statistic. Your p-value is this case. In this case, they're so significantly, different from each other that or I think in this case, they're actually the same from each other, that your p-value is very, very high. If this was different from each other, let's say, for example, your mean was like 3 on this guy for RSV2, we now see that now we have a statistic of this guy, which honestly, you're probably going to ignore it and probably focus more on the p-value. Okay, so you can see it's like, oh, in this case, like the value is so much, they're not significant enough. They're a 0.8 value, so you'd fail to reject the null hypothesis. Okay, that's probably because this size right here, sorry, this scale is actually pretty big. So instead we had something like, let's say, a scale of like 0.5. Let's just do a scale of like 0.1 here. That means the standard deviations are really relatively small. And now we actually have something that's significantly different from each other. You can see this p-value is very, very small and see their difference. And what I have in this function here is basically just comparing the student's t-test and the Welch's t-test. These are the test statistics. You can see the test statistics are very, very like similar to each other because the variation is probably very similar. But even if I had like 500 in here, you can see here, in this case, Welch is going to be significantly different because I have just a huge value in here. The assumption for the student's t-test is going to be different, but you can still see here, we end up rejecting both of them. So the idea here is that this is really all you need to do your t-test right here. And so there's all that buildup just for this tiny little function from SciPy. Okay. But we'll go into more detail about this tomorrow. I know I went through it very, very quickly, but hopefully you guys have an idea of the concept of what a hypothesis test is, the steps of it. It sounds very intimidating when I go through this first part, but really like all it is this guy right here. Like I don't want to fool you into thinking that it's something really, really complex. Like it's really going to be a simple thing. There is documentation on SciPy's t-test and everything. And if you want to, you can look into it. It's not as, in my opinion, SciPy hasn't had as great as documentation as some other packages out there. But basically, you're just feeding in A and B, and then you're getting out the statistic, which is the t-statistic, and the p-value itself. Okay, cool. All right, cool. So that kind of ends everything. How we feel overall? Thumbs up, thumbs down, sideways. Hopefully this like made you guys feel much more reassured. And it's like, oh, that's easy. Like I can do this. Like this is easy. I just have these two populations, and that's why I say the most important part is not actually performing the test, but it's all the stuff prior to actually performing the test and then interpreting those results. Okay, cool, everyone. Well, I'll stop here. I do have to head on to another meeting, but we'll continue our hypothesis test and talk about A/B test and the different like multiple comparisons and warnings next time. That'll technically be topic 14 and topic 15 kind of combined together. I guess actually even topic 16 because topic 16 is A/B testing, but A/B testing is really just hypothesis test. Okay, cool. All right, everyone. Well, I do have to go. I'm going to end it here. I'll see you all tomorrow.